Thank you all for joining this MOPEX webinar, where I will talk about averaging. And on first sight, you might think, how can he talk about averaging for half an hour? How hard can it be? But I think in the course of this presentation, you will find out that there are certain subtleties in averaging that in many situations need some attention. Furthermore, averaging goes down to the bottom of what you're actually aiming at, and that is measuring signals and trying to get the most information out of that. So I'm with a company called HBK, which is a recent merger of HBM and Brule & Kjær. And through this merger, we are capable of covering a wide range of physical domains, ranging from mechanical, sound and vibration to electrical, which are arguably all the domains that you need for electric power tests. My role within the company, as Sam mentioned, is that I'm a senior product owner and I'm covering mostly perception and eDrive. And every now and then I'm also doing some work for the hardware and the embedded software called the Genesis high-speed solution. So we're going to talk about averaging, but first I want to talk a bit about electric power test, what it is and what we are normally doing there. Then I will discuss some basic notions about averaging. Some of them you may know, some of them you may not know. Then I'm going to talk about averaging of processed signals, and I will conclude with observation and conclusions. So first about electric power tests. So what do we mean when we talk about electric power tests? Well, this is an overview that we normally use. So when we're doing electric power tests, we have a quite diverse and quite complicated system, normally consisting of at least one power source, an inverter, electric machine, etc., etc. You might also have a gearbox, what have you. And this is a system that you want to get information from. That is basically what you want. So what you're doing is you're measuring, for example, the power that is delivered by the battery or by some other power source. You're looking at the signals going into the inverter, coming out of the inverter. You're measuring all kinds of electrical signals on your electrical machine. And you normally also measure mechanical signals, for example, the torque and speed of your machine. And on top of that, you may also be interested in how much sound that your motor makes, or how much it vibrates, the vibrations, for example, in the shaft, which may impact the gearbox, etc., etc. And in this process, you are collecting a lot of signals. You collect a lot of data, but also you collect a lot of signals. And those signals, they are measured in a number of different domains. For example, you can have signals measured in the mechanical domain, electrical domain, sound and vibration, etc. And as things nowadays are, those signals are normally sampled. And depending on how you set up your system, all those signals, they may be sampled at a different sample rate. What is normally also done to give you more information on what you are measuring, signals that you measure are processed to obtain new signals to give you different information about what you're measuring. And then after processing, or sometimes during displaying, signals are displayed in a number of different ways, often after processing. And you can think of, for example, showing signals in the time domain. You can process signals in the time domain to move to the frequency domain, spectral domain. You can calculate harmonics of signals. Sometimes it is also useful to show signals in a XY representation or in a phasor representation, DQ0, etc., etc. So you are going much further than just measuring signals. You are also processing signals in order to get a different view on the information that you are measuring. In many cases, it is required or convenient to take the average of signals, either directly measured signals or signals that were processed already, and then you want to take an additional average of those signals. For example, you can do averaging to obtain certain signal properties. For example, you may want to have the DC component of a AC signal, or you may want to have the average power over a cycle of your machine. So all those operations, they need averaging. Another reason to do averaging is to remove fluctuations due to unwanted conditions that you cannot control. So, for example, maybe you want to measure for a long time, and then you want to average over, and the temperature is not constant. And, for example, you want to average to mitigate the influence of temperature changes. And a third reason that you, for doing averaging, might be that you want to reduce the uncertainty in a measured or processed signal. So you measure a entity several times, and then you average it, and then you reduce the uncertainty in your measurement. So there are probably more, but I think it's fair to say that there are many motivations or reasons why you would like to do averaging on the signals that you measure or on the process signals that you have measured. This presentation actually was triggered by questions that we got from customers about how we do the averaging and why we do the averaging as we do it. So this presentation covers averaging in general, but it focuses also a bit on electric power test. But the principles that I will talk about, they are quite general, but definitely useful in electric power test as well. So first, some basic notions about averaging. Most of them you will probably know, but we'll see. So averaging is sometimes concerned with averaging of measured signals. So in signal processing, it is very common to take the average of a continuous time signal, which I can call xt, in the time domain over a certain time interval t. So that is a very basic notion of averaging. And what then happens is mathematically you take the integral of your signal x over time and divide it by the length of your averaging or of your integration interval. If you want to see it in a picture, what you are doing is you're calculating the area under the curve, a famous term, area under the curve. So what you're doing in the picture to the right is you measure the area that is above the horizontal axis and you count it as positive, and you take the area below the horizontal axis, you take that as negative, you sum up all those areas, and that is your integral, and then you divide by the length of your integration time, capital T, and that is your signal average for a continuous signal. So the average of a signal is determined by integrating the signal, often called the area under the curve, and dividing it by the length of the time interval for which you do the integration. So this is, I think, all quite known. And what you get then for that signal is the mean, the average, but it's also called the mean of the signal, or it's also called the DC value of the signal over the time interval t. Now, nowadays we very rarely work with analog signals as soon as you start measuring. So in many cases, the average of the signal is not determined directly on the continuous signal xt, but it's determined on a sampled representation, which we can call x of n. And if you have the analog signal drawn here as the light blue curve, then what you're doing is you're sampling that signal and you get a number of samples, and that is your sampled signal. And of course, time is elapsing when you are doing the sampling, but normally the samples are not counted in time, but are counted in number of samples. And the running variable is in most cases no longer t, but the sample number n. So this is just a representation of a sampled continuous signal. So if the time interval contains n signal samples, the average of the samples is routinely calculated as, well, sum up all the sample values, divide by the number of samples, and that is your signal average. So the average, in the case of sampled signals, the average is the sum of the samples divided by the number of samples. I think also that is straightforward. In this case, the time between each pair of samples is equal. So then when we have this situation, we are talking about equidistant sampling. And when you're working with sample signals and you want to take the average, most people don't give it a second thought. They are just summing up all the samples and divide by the number of samples. But if you think a bit deeper about this, then you can ask yourself, okay, looking at the continuous signal, I'm looking at the area under the curve, and then I divide that area under the curve by the time that I measured. But if you look at sampled signals, samples don't have a width, so they are existing only in a very short moment in time. So you can then ask yourself, why does the sum of the samples divided by the number of samples, why does that approximate the average of the continuous signal? Well, if the sample time is delta t, then the time interval t that you use for averaging your continuous signal can be approximated by n times delta t. So n times delta t covers the time, the same time approximately as that you used for finding the average of your continuous signal. And you can estimate the area under the curve by saying, okay, for a sample, I take the area, this area, for example, when I have this sample, I say, okay, this sample is valid from the time that the sample occurs until the next sample, and then I approximate the area under the curve by adding all those rectangles. And that is then an approximation of the area under the curve. And that looks like this, like this. So the area under the curve can be approximated by multiplying every sample value that I have by the sample time. And since the delta t does not depend on I can take it out of the summation. So the area under the curve is approximated by the sum of the samples times the time between the samples. That is how you can approximate the area under the curve. You can also do it in different ways. For example, you may think that you can also, for example, not take, for example, this rectangle here for the first sample, but you approximate it by a shape that goes straight here, a straight line here, and then here, and you can calculate the area for that shape and the same area for that shape. But let's, for the moment, stick with approximating the area under the curve by the sum of those small rectangles. So that is the area under the curve. And so now, like I did with finding the average of a continuous signal, I can divide the approximate area under the curve by the time. So we are doing the same as that we did with continuous signals. And then I get the area under the curve was delta t times the summation. The time was n times delta t. And now we see that the delta t cancels out. So indeed, when talking about sampled signals, the approximation for the average is indeed the sum of the samples divided by the number of samples. So nothing new here, but it gives a bit of insight, I think, in why this commonly used expression is a good approximation for the average of the analog signal. But we should notice here that the delta t cancels out because the distance between the samples is equal. So we can simply take the sum of the samples and divide it by the number of samples in this case. But that is only allowed here because I am dealing with a sample signal that is equidistant. So the time between all of the samples is equal. So if I don't have that, so if I have a sampled signal, but the time between the samples is not equal, then I can use the same approach at least to approximate the area under the curve, but then I have to do it differently. If I want to get a good approximation for the area under the curve, then I have to take into account the time between two samples. So what I see in the picture here to the right, my delta t is not fixed, but it varies over time. So what I then should do in order to get an approximation for the average of such a kind of non-equidistant signal, I get a more complicated expression. So what I do is I still add the area of all those rectangles, which is for the ith rectangle is xi times the time of that sample, so ti. I have to sum them all up, and then I get the total blue area, and I have to divide it again by the total time. And that is now not n times delta t, but I have to add all those individual time distances between the samples. I have to add them all separately. So when my signal is sampled, but it's not sampled in an equidistant manner, calculating the average is not straightforward. So you have to do something that is more complicated. So again, for equidistant sampled signals, this is never a problem. And you can simply add the samples and divide by the number of samples. But that is not the case when you have sampled signals that are not equidistant. So what I talked about up until now is we were looking at a signal that is being sampled either in a equidistant manner or in a non-equidistant manner. So that is one form of averaging. Well, one of the other reasons that I mentioned before to take the average is to get a better estimate of an entity or of a measured value or of an observation or whatever you want to call it. And that is something that you, for example, do when you measure a weight with a scale that is not very accurate, and every time you measure a slightly different weight. And then in order to get a better approximation of the actual weight of what you're measuring, you do a number of measurements and then you average them to get a better estimate. For example, if a measurement, for example, the cycle RMS is measured with a certain uncertainty, averaging several measurements, measured values will reduce the uncertainty. So cycle RMS or weight or whatever measurement you are doing. And you may want to use that to get a better measured value, for example, for a test value, for a set point value in your test setup, or to get, for example, a better or more stable value in a meter or whatever. And if you have n measurement values, xn, the average of the measured values is given like this. So the difference here, well, this is the same expression as we saw in taking the average signal value of an equidistant sampled signal, but the situation here is different. So the question is, do we really measure signals? I'm talking here about making observations of a physical entity. So I measure something or I do an observation. And in that case, I use this formula. So I just add all the measured values and I divide by the number of measurements that I've done. So the expression is the same as for equidistant signals, but the situation is different. So this is the same expression as for averaging signals. Now, so now basically I have laid down the basic ideas of averaging of signals and averaging of observations, which are similar but still slightly different. So what you often do in electric power tests, many entities in the electric power tests are best measured on a per cycle basis. For example, if you look at harmonics, in an earlier webinar I was talking about IEC 61000-4-7 standards. What you do there is you measure harmonics over one or multiple cycles, but you always want to have an integer number of cycles that you are doing your processing on over. So, for example, harmonics is a good example. In many cases, you also want to measure the power, electrical and mechanical power, over a single cycle or over a single revolution of your machine. And similar to that, you also want to calculate the efficiency, which is based on powers. You want to calculate the efficiency over an integer number of cycles, normally 1 or 2 or maybe 10 or whatever. But you always want to measure, or you normally want to measure over an integer number of cycles. When you do that, when you do cycle-based processing, it is done on an input signal and it generates a new output signal. So for every cycle or for every 4 cycles, you get a new data point, because that data point then says, okay, this was the RMS value for the previous 4 cycles. So you get a new sample value. And then for every cycle or for every group of cycles, you get a new sample. Because those processing, this type of processing produces a result for each cycle or for every 4 cycles. But when you're measuring a real life setup, the cycle time is not fixed. And this will lead then, of course, to signals or that have non-equidistant samples. So the time between the samples is not equidistant. So you are generating from your equidistant signals by doing certain processing, for example, determining the cycle RMS. You're getting a new signal which is not equidistant. Now suppose that you want to determine a set point value of an E-drive setup, and you want to combine several cycle-based values to get a better result. That is something that you will often see in practical situations. So you have a raw signal or equidistant signal, you have processed it such that you get a new signal depicting the cycle RMS or the cycle-based power, and you want to average several of those samples to get a better value. To get a feeling of how to combine cycle-based results, we will consider 3 different cycle-based properties. First, we will talk about the processing is done to get the cycle mean of the signal. Then we will talk about the cycle RMS of a signal. And then we will talk about the cycle maximum. So the first one, you have a processing block that determines the the mean of a signal over a cycle. The second one is a processing block that determines the RMS value over a cycle. And the last one is a processing block that calculates the maximum value over a cycle. Well, where you should keep in mind that all the cycle times may be different for all the values that you get. So the different measured values are represented as a asynchronous or non-equidistant time signal. So the time difference between the samples, so the RMS values and the maximum values, is in general not fixed. So that is the situation that we're looking at. So we have seen that when taking the average for non-equidistant or asynchronous time signals, we have to take a weighted average. So that was the more complicated formula that I showed. So the question is this also true for the signals representing measured signal properties? And what does that mean then? So what we are now looking at is we are looking at a new signal which contains non-equidistant samples. And we are going to average them. So it's but how should we do that? Should we do that weighted or should we do that not weighted? Okay, just let's try to get a feeling for that. So first we are going to talk about the cycle mean. So your processing block is a cycle mean, and for the sake of argument, we say that we are calculating the cycle mean over a single cycle. And in the picture to the right here, we have the first sample is the cycle mean over the first cycle, and the second sample is the cycle mean over the second cycle, and the third sample is the cycle mean over the third cycle. So that is what we have. So this is our non-equidistant signal. So what now happens if we take the non-weighted average of those samples? So we just take the sample values, add them together and divide by the number of samples. Well, if you look at what that means, it gives you an improved estimate of your one cycle mean, because you are doing 3 observations of the cycle mean, albeit with slightly different cycle duration, and you're averaging out the variation in cycle duration. And so what you get in the end is an improved estimate of your cycle mean. But this is a non-equidistant signal. So we said before, well, maybe it's better to take the weighted average. So the weighted average of the cycle mean gives me the average or the mean of the signal over all used cycles. And it's good to note that those things are different. So, for example, if I have a signal here, so in this case I have 2 cycles, what I can do is I can calculate the mean over the first cycle, and I can calculate the mean over the second cycle. That's basically what I've done here. And I call this mean 1 and I call this mean 2. And the other situation is I can calculate in one go, I can calculate the mean over those 2 cycles, and that is what I call the mean. If you now go through the math, then you see that if I take the non-weighted average of those 2 mean values, written here, mean 1 plus mean 2 divided by 2, that is not equal to the mean that I measure here. If I take the weighted mean, so I weigh the mean 1 with the number of samples that I used to calculate mean 1, and I weigh mean 2 with the number of samples that I used to calculate mean 2, and I divide that by the total number of samples, then I get the mean. So if I take the weighted sum of those samples, that is the same as the average, the mean, over the whole period, over the whole time period that I was averaging over. So in this case, the weighted average of cycle mean still has a quite clear physical meaning. It is the mean over the whole time that I was looking. So not so much special going on in averaging cycle mean values. Now we're going to look at the cycle RMS. So we have a processing block that calculates the RMS value over a single cycle. And again, I have samples produced here, and they are not equidistant. Now again, I have the option to use the non-weighted average of the cycle mean values. And again, that gives me an improved estimate of a single cycle RMS value, because I'm just averaging observations. Now, the weighted average of cycle mean values, if I look at that, that is not so easy to interpret what that means. But one thing is sure, it is not the same. So I'm taking the weighted average, but even then it is not the same as the RMS value calculated over all involved cycles. This was the case with cycle mean, but it's not the case with cycle RMS. So again, I'm calculating the RMS value over the first cycle, over the second cycle, call them RMS1, RMS2, and I take the RMS value over both cycles together. What I now get if I average non-weighted averaging of the RMS1 and RMS2, that is not equal to the RMS value that I calculate here. If I use the weighted RMS value, it's also not equal to the RMS value that I get when I would have averaged over 2 cycles. So the interpretation of the weighted average for cycle RMS is not so clear. For cycle mean, it is clear, but for cycle RMS, it is much more complicated. The non-weighted average is much more clear. It just gives you a better estimate. So the situation with cycle RMS is fundamentally different from the situation with cycle mean. Now we are making it even worse. We are going to cycle max. What does the non-weighted average of cycle max values mean? So I measure them max over a single cycle 2 times, and then I average them. What does that mean? I don't have a clear notion about it. I can think of something, but it's not so clear as with cycle RMS. And what does the weighted average of cycle max values mean? Even less clear, I think. So again, the situation that we have, we are calculating in the left picture, we're calculating the maximum value over the first cycle and the maximum value over the second cycle, here and there, maximum sample values over, and I'm for N1 and N2 samples, call them max1 and max2. In this situation, the max value is obviously here, but the average, either weighted or unweighted, of those 2 samples has nothing to do with this maximum value. So the interpretation of both the weighted average and the non-weighted average is difficult. So it's not trivial. So this leads us to some observation and conclusions. Although averaging might seem quite trivial at first sight, in reality, there's a bit more going on than you may think. So taking the average of signals is intuitive. Over a given time interval, you take the sum of the samples of the sample values divided by the number of samples, and this is routinely done for quantized, directly measured signals. So you have an analog signal, you sample it at a fixed sample rate, and that's it. And you can very easily find the average. In contrast, averaging non-equidistant processed signals requires careful consideration. You really have to think about what does it mean if I average over 4 cycles or if I take the non-weighted average over a single cycle. So you have to think about it, and there's not, let's say, one silver bullet answer. Non-equidistant signal samples are often cycle-based signal properties, and a non-weighted average of such values often gives a better estimate of the property. for example, cycle RMS. Not all non-weighted averages make sense or have a clear meaning. Maybe they have, but you have to ask yourself, okay, what does it mean then? If I take the non-weighted average of non-equidistant processed sample values. Weighted averages are often hard to interpret. And for asynchronous signals, in many cases, the non-weighted average makes the most sense. But always carefully consider what the average of a certain asynchronous signal means, and also consider to not take the average. In some situations, it is better to not take the average, because that may actually give you what you want. That is basically what I had to tell about averaging. If you want to subscribe to our YouTube channel or our LinkedIn group, please feel free to do so. And if you have questions about this topic, then you can always contact me. Thank you.